Right, so we know how to fill in the table. We know how to arrive at the minimum number of multiplications, which in this case happens to be 9375 something. And we also know this about a dynamic programming question, that it will always give you a number as the solution, and that number will be the optimal value, the maximum or minimum, whatever you're trying to find out. It will not give you the actual configuration of parameters. For example, in your CCP, the table will not directly tell you which coins you're taking and which coins you're not taking. In your longest common subsequence, the table will not directly tell you which characters are part of the sequence or what is the longest sequence. You had to do some manipulation, such as inserting arrows or whatever, to find out that configuration. So here, when you look at matrix chain multiplication, obviously the configuration of parameters which you're trying to find out is which order I'm going to multiply or where to place the parenthesis. So when you put the parenthesis around, say, A2, A3, you know you're going to do A2, A3 first and then multiply A1, whatever. So if you want to know the order in which to multiply, you need to be able to place parenthesis appropriately in this expression. So that is what the backtracking is going to teach us how to do, and it is for the purpose of this backtracking that we have kept a record of these k values. So otherwise, if you just want the minimum multiplications, it is just the numbers in the grids. The k value is just there for backtracking. So those of you who are familiar with the longest common subsequence example will know that apart from the numbers in the grids, I also put arrow marks there, and those arrows guided us in the backtracking. Similarly, here these k values are going to guide us. So we'll start by seeing how to backtrack. So for this example, the backtracking is a little vague in the sense that if you take longest common subsequence backtracking, you have a clear path of arrows. You just follow the arrows and go. If it's a top left arrow, you jump top left. If it's an up arrow, you move up. If it's a left arrow, you move left. You just simply follow the path. Here it is not as simple as that. You will have to go to one grid, break that, jump off, go to another grid. There's a little bit of jumping around which is needed, but we'll go with this example itself and we'll try to understand. So you start by putting the entire sequence in parentheses, A1 times A2 times A3 times A4. Now we will continue to insert parentheses until each individual matrix is enclosed by braces. So that doesn't mean you simply make it A1 within braces times A2 within braces, appdi illa. So there is a sequence of steps we will follow until every matrix becomes an individual matrix. We will continue to enclose parentheses according to a bunch of rules, and that will give us the optimal order. So first, we, as always in a DP solution backtracking, you start from that grid which gives you the solution, the final solution. So here it is the top right grid. So you start there, you look at the k value which is 3. So you will put parenthesis after 3. So up to 3 you will split it into one bunch, and from the next one onwards you will split it into another bunch. So here it's a 3. So A1, A2, A3 is one group and A4 becomes another group. So this is the first split we have done. Now if you see here, A4 is a singleton matrix, so it just exists. You don't need to find any optimal order for that. But A1, A2, A3 again is a sequence of matrices. So within that you can do A1, A2 times A3 or A1 times A2, A3. So there is an ambiguity there. So again for this subsequence you have to find the optimal order. So now you take this sequence, it is A1, A2, A3. So you will go to this table of 1 of 3. Obviously the starting matrix becomes your I value, the ending matrix becomes your J value. So you will go to the same I, J coordinates. You look at the K value there again, it is a 1. So you will put a bracket after A1. So you had A1, A2, A3 times A4. Within that A1, A2, A3, A1 becomes a separate part and A2, A3 is another part. Now A1 is a singleton matrix, no need to worry about it. A4 is a singleton matrix, no need to worry about it. A2, A3 is again a sequence. So your I is 2, J is 3. You go to 2, 3. You see the splitting point or the k value is 2. So after A2 you will put a bracket, A3 becomes another team. So A2 cross A3 is split into A2 times A3. So this is the final order of parenthesization, which means you will first take A2, then A3, you will make it A2, A3, then you take A1, you make it A1, A2, A3, then you take A4, you multiply A1, A2, A3 by A4. That is the optimal order in which you have to multiply. and your if you multiply in this sequence, you will end up with just 9, 3, 7, 5 multiplications. Any other sequence in which you multiply will end up with more multiplications than this. This is a summary of your matrix chain multiplication. So backtracking alone I'll explain again quickly. You start by putting the entire sequence into parenthesis. Your first matrix is always represents the I value and the last represents j value. So go to dp of I of j, look at that corresponding k value, you split it up to the kth point and from k plus 1 up to j. So whenever one split gives you a singleton matrix, you will ignore that from now on because there is nothing more to be done with it. Whenever you have a sequence of matrices, whether it's 2, 3, 5, 8, whatever number of matrices, again your starting point is A, ending point is J. So you go to the corresponding cell, again you find the K, you will split it over there. You continue this until every split becomes a singleton matrix. Now you know this is the final sequence.